Now that we know how to draw Newman projections, let's see if we can apply that skill to different conformations of butane. So if I have butane right here, and I'm going to stare down the carbon 2,3 bond this time. So here is my I, like that, and I'm going to stare down the carbon 2,3 bond. So let's see if I can draw a line showing you that carbon 2,3 bond. So we're going to stare down that carbon 2,3 bond and draw a Newman projection of what we see. So my first carbon of course would be this one right here. So this is the first carbon that I'm going to see. So for my Newman projection, that would be a dot. And then I have a hydrogen going up and to the right. So here's my hydrogen going up and to the right, and that was actually this hydrogen right here. So this hydrogen is up and to the right. I have a hydrogen going up and to the left. So let me go ahead and draw that hydrogen in on my Newman projection. So hydrogen going up and to the left, and then I have a hydrogen going down relative to that plane. Sorry, not a hydrogen. I have a methyl group going down relative to that plane. So let me go ahead and put in my methyl group going down. So there's my methyl group like that. My back carbon would be, of course, this carbon right here. So let me go ahead and draw on my back carbon. What is connected to my back carbon? I have on my back carbon a methyl group going up. So let's go ahead and put in a methyl group going up here. I have a hydrogen going down and to the right. So let's go ahead and put in my hydrogen going down and to the right. And then I have another hydrogen over here going down to the left. So let's go ahead and put in the hydrogen going down to the left. And here I have a staggered Newman projection for butane, sliding down the carbon 2,3 bond like that. Let's go ahead and rotate and get a different conformation here. So I'm going to keep the back carbon the same, and I'm going to rotate the front carbon. So I'm going to keep the back carbon the same, and I'm going to rotate the front carbon. So I'm going to take this methyl group, and I'm going to rotate this front carbon all the way over to here. So if you have your model kit, go ahead and take it out, and you'll definitely need to use it to see all of these different conversions here. So I still have a Y for my front carbon there, and this time my methyl group has now moved over to this position, and that makes these guys over here 2 hydrogens. The back carbon I kept the same, so the back carbon didn't move, so my methyl group is right here, and then these 2 guys are hydrogens as well. So that's another conformation for butane. I'm going to go ahead and rotate the front carbon again, right? So I'm going to keep the back carbon the same. I'm going to rotate this methyl group over here to get yet another conformation of butane. So I still have a Y for my front carbon. The methyl group has moved over here, and now I have my 2 hydrogens like that. And my back carbon still has a methyl group and 2 hydrogens. So these are all staggered Newman projections of butane. And I need to think about the stability of these 3 Newman projections. Which one of these 3 Newman projections is the most stable? Well, if I take a look at the first conformation here, I have 2 methyl groups, right? So here's a methyl group and here's a methyl group, and those 2 methyl groups are 180 degrees from each other. So you could say their torsional or dihedral angle is 180 degrees, and that is called anti. So those 2 groups are anti to each other, 180 degrees torsional angle. And methyl groups are very big and bulky and have lots of different electrons that repel each other. So keeping them as far away from each other will give you the most stable conformation. So actually this first conformation, the anti-conformation, this is the most stable for these staggered conformations of butane. If I move over here to the second conformation, I have 2 methyl groups that have a torsional angle of 60 degrees between them, right? So anti was 180 degrees between my 2. Here I have 60 degrees between my 2 bulky methyl groups, and we call that gauche. So we have a gauche interaction between my 2 methyl groups. And obviously things that are very big and bulky have steric hindrance, right? So 2 methyl groups really close together, that's going to destabilize the molecule. Bulky stuff gets in the way, which is steric hindrance. When you calculate the strain, you get an additional 3.8 kilojoules per mole of strain from a gauche interaction of 2 methyl groups. groups, which obviously destabilizes the molecule. And when I look at the third example, once again, I have two methyl groups 60 degrees to each other. So this is also gauche. This is a gauche staggered conformation of butane. So this also has 3.8 kilojoules per mole of energy, which destabilizes the two gauche interactions compared to the anti-interaction. So this is actually going to be the most stable for all of these guys right here. And when you have two molecules that have the exact same energy, right, 3.8 kilojoules versus 3.8 kilojoules, we say that the two conformations to the right are said to be degenerate since they have the same energy. Well, those are the Newman projections for the staggered conformations. What about the eclipsed conformations of butane? So if I were to rotate to get an eclipsed conformation of butane, let's go ahead and think about what that would look like here. So I could have an upside down Y in the front. I could put my methyl group here. I could put my two hydrogens here, and then for the back, I could have my methyl group eclipsing the other methyl group, and then I could have my two hydrogens and my two hydrogens like that. So that's one possible conformation in the eclipsed conformation, and I could interconvert that eclipse conformation to another one. So I'm going to rotate the front carbon. Okay, so I'm going to rotate the front carbon, and I'm going to move this methyl group all the way over to here. So if I keep the back carbon stable and rotate the front carbon, right? So if I rotate that guy 120 degrees, I'm going to put the methyl group over here now, and now I have hydrogens. So follow along with your molecular model set is the easiest way to do it. And then in the back there, I'm going to have a methyl group, and I'm going to have those hydrogens which have not moved. So that's another possible conformation. In the eclipsed, I can draw another eclipsed conformation, right? I could take this methyl group and I could move it all the way over here. So let's go ahead and draw that for my third version. So here I have my upside down Y. I'm going to put my methyl group over here this time, and so my hydrogen would go here, hydrogen would go here. Again, I kept the back carbon the same, right? So this is still going to be a methyl group right here, this is still going to be a hydrogen, and this is still going to be a hydrogen. So here I have my three eclipsed conformations for butane, and let's think about the stability of these guys. Well, in my first example, right, in my first example over here, I have two very bulky methyl groups which have a torsional angle of 0 degrees between them. And huge groups, right, steric hindrance are going to destabilize. So you actually get torsional strain, from these electrons repelling these electrons, and you're also going to get some steric strain from the steric hindrance of these bulky groups. And when you add all that together, the torsional and the steric strain, you end up with about 11 kilojoules per mole. So when you have two methyl groups interacting together, you have about 11 kilojoules per mole of energy, making it much higher energy, right? Two hydrogens eclipse we saw in the last video, that gives us about 4 kilojoules per mole. So if you're calculating the total potential energy of butane, you're going to get 11 plus 8, so you're going to get 19 kilojoules per mole for this conformation. I move to my second conformation, and I have here two hydrogens interacting, so that's going to be 4 kilojoules per mole. We saw in the last video that a hydrogen and a methyl group eclipsed will give us 6 kilojoules per mole, and so this is also 6. So when you add all that together, you get 16 kilojoules per mole for its total potential energy. And over here on the right, same thing, right? I get 6, and I get 4. So this is also 16 kilojoules per mole, so degenerate in terms of energy. So the two on the right have the same potential energy. They are more stable than the conformation on the left, which has the two methyl groups eclipsing each other, destabilizing that molecule. Let's draw another molecule, so similar to butane, except this time we're going to put a methyl group coming off of the butane carbon chain. So this time we're going to have a methyl group coming off of this carbon right here. So we'll make that a methyl group, and we'll make that a hydrogen. And then same idea, right? This would be a hydrogen right here, and then this would be a hydrogen right here. So that's 2-methyl-butane. So we're going to do the same thing, right? We're going to stare down the carbon 2-3 bond. So we're going to look this way, and we're going to go ahead and let's put a line in here indicating the axis that we're looking down, right? So something like that, All right, so that's sort of what we're looking at here. And let's see if we can figure out the Newman projection. So let's say the question is draw the most stable conformation for 2-methylbutane. So the most stable conformation has to be staggered, right? So let's go ahead and draw the 3 staggered conformations. Let's see which one of those 3 is the most stable. So as I stare down that carbon, right? So here's my first carbon. So let's see what is attached to that carbon. Well, there is a methyl group going down, and that's this methyl group right here. And then I have a methyl group going up and to the right, which is this methyl group over here, and then I have a hydrogen going over here in this direction. All right, my back carbon, what is attached to the back carbon? Well, I can see that I have a hydrogen going down and to the right, a hydrogen going down to the left, and a methyl group going up. So a hydrogen going down and to the right, a hydrogen going down and to the left, and then a methyl group going up. So that would be one possible conformation staggered for 2-methylbutane. All right, this time I'm going to rotate the back carbon and keep the front carbon stable. And you can do any one you want. For me, it's just easier to keep the front carbon stable because the front carbon already has 2 methyl groups on it. The back carbon only has 1 methyl group on it, so it's a little bit easier. So let's think about rotating the back carbon. And we're going to rotate it. Let's take this carbon right here, so the back one. We're going to rotate that carbon over to here. So let's go ahead and draw that conformation. So we still have a staggered conformation. We moved our methyl group over here, so these would be hydrogens now. And let's draw one more staggered conformation. Right? Let's rotate the back carbon again. So we're going to take this carbon and we're going to rotate that carbon over to here. So let's go ahead and draw that Newman projection. So again, the front carbon we're going to keep the same, and so that has 2 methyl groups. The back carbon we just rotated to move the methyl group over to here now, and this is still a hydrogen, and then this must be a hydrogen as well. So let's compare these 3 staggered conformations, Newman projections, and let's see which one is the most stable. So let's look at what sort of interactions we have here. So here I have one gauche interaction, right, between this methyl group and this methyl group. So I have a gauche interaction there. So that's one gauche interaction, and we saw in the earlier example that a gauche interaction will give you an additional 3.8 kilojoules per mole of strain. All right, so let's look at this. The second conformation. Here's a gauche interaction, and here's a gauche interaction. So there are actually 2 gauche interactions for the second conformation, right? So each one would give you 3.8 kilojoules per mole. So when you add that together, right, you're going to get 7.6 kilojoules per mole for this one. And our third conformation, if I look at this, I have only 1 gauche interaction. And that's it. So only 1 gauche interaction for this guy. And so that would be 3.8 kilojoules per mole. So 3.8 kilojoules per mole. So out of these 3, right, which one is the most stable conformation? Well, we have 2 that have the same lowest energy. Remember, the highest energy is the least stable. So this one in the middle with 2 gauche interactions that destabilizes the molecule. So the molecule is going to spend the least time in the center staggered conformation. Whereas these 2 on either side, right, this one over here only has 1 gauche interaction, and this one over here also only has 1 gauche interaction. So those would be your most stable conformation. So they are degenerate, obviously, because they have the same potential energy value.